It's probably the hardest, I think, out of all of the analytical chem components, purely because it doesn't make sense logically. Scientifically, it makes sense, but it's difficult to sort of put it together in the brain, right?
Yeah. Oh, but for X-ray crystallography, we don't really need to know that, do we? We did that, like, no. I'm going to say we gave it 5 minutes in class.
Yeah.
Pushing it.
Well, we could go over X-ray crystallography because it's pretty simple.
Yeah, okay.
Nowhere near as complex as mass spec. So what we're doing here is, by doing this, we're actually going to destroy the sample. So it's used to analyze. It's not used to separate or to study. It's used to just figure out what's there. But once you figure that out, you've lost your sample. So it's not always appropriate for everything. So we expose the sample to a very high level of electric charge, effectively. We used to use this in the lab to separate blood samples. So what we were looking for is we would take the sample of a person that was not having a heart attack, just a random person in hospital who had perfect cardiac health. We'd take, I don't know, 1,000 of those samples, and we put them all together and figured out what was normal. Then you get a call from the emergency department that somebody was presenting with heart failure symptoms or heart attack symptoms. So they would take a blood sample, run it through the mass spec again, and compare these results with what was considered normal. And by doing this, you could see what was different in the blood in someone that was having a heart attack. So what you could theoretically do with that information is come up with effectively a blood test that uses mass spectroscopy, and you can diagnose heart failure or any kind of heart condition, virtually within 20 minutes or so of taking the blood sample. Now it takes hours, and oftentimes you're losing tissue and losing brain function while that's happening. So the mass to charge ratio is what we use to determine the fragments that are there. It's recorded on a mass spectrum, which looks like this. The two most important parts are the base peak and the molecular ion. The difference here is in your, when we looked at chromatography, the height of the peak told you the concentration, whereas with this, it's the relative intensity compared to all of the other fragments. So it's a little bit different to the mass spec, to the chromatography, chromatograph. So we run our ethanoic acid through our mass spec, and what happens is, because we are ionizing it, we're creating lots of different molecules. All of them have a different mass to charge ratios, and we get a spike. So one of those will be the loss of the CH3, so we end up with just the carboxylic acid group. The other one will just be CH3. Another one will lose OH, and we can analyze what is there by the fragments that we end up with, if that makes sense. I don't think you'll be asked to do anything other than tell what, maybe the size of an alkane. Usually, if they're wanting you to figure out something more complicated, you'll get the IR spectroscopy with it, and you can usually tell by the IR spectroscopy what it is. So, base peak, the most abundant, it's got the highest relative intensity. Its relative intensity will always be 100. So, the highest mass to charge ratio, again, which is on here, is the molecular ion. Now, with the molecular ion, it is whatever was present there before minus 1 electron. So that tells us that the molecular mass of that compound is about 72.
Okay. So if they give us like the molecular formula, and then they like determine the empirical, or if they just say determine the empirical formula of, or no, sorry, determine the molecular formula of this. Like, I don't, like 72, that could have like an innumerable amount of possibilities. Do you know what
So
I mean?
that's why we look at other things as well.
Okay.
So here you've got the fragment ions and their mass to charge ratio. Not particularly helpful, I don't think. So the mass of the molecular ion is the same as the parent molecule. That's the key thing to remember here. So have you been given any practice questions for this?
Yes, I think so.
Did they give you the infrared spectroscopy with it as well?
I
Just
think
the- Yeah.
there's been a combination of like different types, but some with, some without.
So ethanoic acid. So the molecular ion loses an electron. So it becomes CH3COOH plus.
Yeah. Okay.
So we look. So if you add up the molecular formula of, so what will likely happen in the exam is you are given an IR spectrograph, which will allow you to determine what functional group is present.
Yeah.
You can then look at, and the classic one is ethanoic acid, because it's not too difficult to figure out.
Okay. Yeah.
So if you go to the formula book, let's say we were given this in an exam. Open up the formula book. Now, time. So we go to, I'm pretty sure I have the formula. Am I going mad? Yeah, I know, that's multiple bonds, technically. We got the infrared data. Have I gone mad or they don't give it to you anymore?
Infrared.
No, they give you the infrared, they just don't give you the.
No, they give you the infrared too on page 14.
Yeah, I can see the infrared, but do they give you the, I don't think they give you this.
Oh, no.
A lot of the time in the question, they might actually give you this.
Okay.
So let's say we've looked at our IR spectrograph and we know it's a carboxylic acid.
Yeah.
So we go to the mass to charge ratio and we go to the far right. It has and this is probably not the way they would have taught you, but this is the way that I think it's probably the easiest. Go to the far right, the highest mass to charge ratio. Figure out what the molecular mass is. Figure out the molecular mass of CH3COOH, which is 60. If it's higher than that, add some carbon and hydrogen. And it'll tell you that it's ethanoic, propanoic, butanoic, whatever. You just have to map, or if it's lower than that, take one away.
So I should just remember, like, as a thing, the molecular mass, I mean, I can calculate it, but like ethanoic acid is a good starting point.
Yeah, if you remember the ethanoic acid is 60 with a carboxylic acid. Again, I've never seen them test anything other than carboxylic acids. They also might ask you to calculate the mass of the carbon chain length of an alkane, which we'll do later on in this. Okay. So we've got a molecular ion peak of M/Z is 86. So what does that tell us about the molecular weight of our alkane?
It's going to equal to 86.
It's going to equal 86. So generally, alkane, we've got carbon. The number of carbons, or the number of hydrogens is equal to 2 times the carbons plus 2 for an alkane.
Yeah. Okay. Oh, so then do we have to do algebra?
So we've got, so the molecular weight of carbon is 12 and hydrogen is 1. So we utilize a little algebra skills. 12 times n plus 1 times 2n plus 2. This is more likely going to be the kind of question.
So it'll be 6. So it'll be C6H14.
Perfect. So it's hexane. So we're just using, again, like pretty much everything in chemistry, we are using basic algebra. Rearrange, solve, and C6H14. When we substitute the 6 back into N, 6 carbons, 2 times 6 plus 2 hydrogens gives us 14. All right, take 17 seconds to figure this out. And this is what was taught this year. They didn't teach ethanoic acid this year, so fingers crossed this will be the kind of question we're going.
4. C4H10.
So
That will be butane.
very good. So again, I can't imagine they're going to put an ester onto this. That would be horrific. So do we remember our isomers? So some ethyl methanoate and methyl ethanoate have the same molecular formula, don't they? But they'll produce slightly different, well, actually quite different, depending on which way around they are. So it depends on the position of the double bond. Likely kind of questions you'll get for this is you'll get given these two and then you'll have to say, well, that's either an isomer or they have the same molecular formula. That kind of thing.
Yeah.
So fragment in different ways, different peaks on the graph. The fact that they don't give you this in the formula book says that it's not going to make up a huge portion of the exam. And if they do put it in there, they'll likely provide a lot of the information that's required because it's not in the formula book.
Okay.
So the whole idea is with this, we can use the fragment, what's the word? The fragment fingerprint to identify what the substance is. So I think you're less likely to get a question like this one, where you have to identify an unknown compound only from the IR spectroscopy. I mean, only from the, oh my gosh, my brain. Thank you. The mass spectrograph. You'll either have to identify a situation in which you could use this to solve a problem, or you would need to have, you would be given the IR spectrograph as well, which would allow you to identify what the molecule is. Then you can use the molecular mass to actually identify exactly what it is, like in the case with the ethanoic acid.
Yeah. Okay.
So if it was, okay, let's say you identify that it's a, oh my gosh, a ketone or an aldehyde. Oh my God, you can go to use the IR spectrograph to figure out if it's a amine, ketone, aldehyde, whatever. This is my first session of the week, so my brain's still getting warmed up a little bit. Although I'm very excited because I don't have any more general maths tripping this time. So.
Oh, because it's the exams today.
Yes, couldn't be more happy with that. And then once you've identified what it is, go to the furthest mass to charge ratio on the right, and then you can use that to identify the molecular mass of what the molecule was, and then a little bit of process of elimination to figure out what the actual, whether it's ethanoic, propanoic, propanol, ethanol, ethanone, that kind of thing.
Yeah.
I'm sure there is another way, but I just think that's the easiest way.
Yeah.
I just think overcomplicating something that's already pretty complicated, it's not particularly wise. Does that make sense?
Yes, it does.
So I think this is one of those things that as long as you understand what it is and you can use the process of elimination, then that's fine. You don't need to know, especially if you're not planning on studying chemistry. One thing you might get a multiple choice question or some kind of part of a question is the isotopes. So remember what an isotope is?
Mm-hmm.
So same number of protons, differing number of neutrons. So I think the example they use is chlorine. Yeah, so chloromethane, you might get some strange looking peaks. And the explanation is the fact that one of the chlorines contains 2 additional neutrons. So its mass number is 37, whereas regular chlorine's mass number is 35.
Yeah, okay.
So that's why if you have isotopes, you'll get a slightly different. Okay, we're not going to look at the fluorine question. So what is the relative molecular mass of this compound here?
114.
Yeah, 114. So what's 114 is the MZ and the relative molecular mass. What would the formula for the fragment ion with the MZ value of 85? So it's an alkane. Using that formula that we used before.
Oh yeah. So CN. What if it gives you a decimal?
What's the decimal?
5.9.
Round it up.
Okay, so it'll be 6, so it'll be C6H 14.
Perfect. So why do we have these 2 peaks here?
Isotopes.
Yep. So what's the likely so bromo-alkane. So yeah, we've got two different isotopes of bromine.
Mm-hmm. Explain why.
Yeah, I mean, we'll just say because we've got isotopes.
Yeah. Okay.
Yeah, okay, cool. I don't think you're going to get anything other than the alkanes. And if you do, it's going to be not so much determining, but, what could you use or process of elimination why do we have two different peaks at this M to Z ratio?